Who are you? What, how, when, where, and why are you? What are you made of? How did you get here? When did you get here? Where are you? And why are you here? We're looking at what you are or what you're made of. Well, you have a physical makeup with all your physical traits, but you're more than just your physical traits. You have a mind, you have ideas, you have dreams, and have all sorts of activities, all things that you do over and above what you're made of in terms of your physical makeup. Girls, sugar and spice and everything nice, for instance. But your physical makeup, well, you are actually made up of over 65% water. Water is a molecule with 3 atoms, 2 hydrogen and 1 oxygen, H2O. You have other atoms too, very important. Carbon, for instance. It can combine with atoms of other elements and itself to make very large molecules, which is important for you in most complex life. Now you're mostly made up of hydrogen atoms. You get more hydrogen atoms than any other atom. And your atoms are made of negatively charged electrons surrounding a nucleus composed of protons and neutrons. Normally, there's as many protons as there are neutrons, and electrons as there are protons. The one exception being hydrogen, which just has 1 proton and 1 electron. Now, if you're in a room and no one notices you, and you can't be heard, and you're getting angry, you think you want to blow up. My advice is to cool it, keep calm, because if you're all mostly composed of hydrogen atoms, and hydrogen is a very dynamic gas. They used to use it in airships because it's the lightest element. But the airships, the Hindenburg, blew up, so now they have to use helium, which has 2 protons, 2 neutrons, and 2 electrons. So keep it cool. But why do you think that no one notices you? You can't be heard. Well, if you look at the size of the the size of the nucleus of an atom, to the size of the atom, is like the size of a speck of dust is to a football field. So you are mostly space. You're 99.9999999% space. So you're nothing at all, really, virtually nothing at all. So maybe that's why you can't be seen or heard. But your atoms can be broken down further as well. Now you may be in that room or not in that room, but you have days where you're elated or days where you're depressed. You have your ups and downs, in other words. Well, physically, you're all up and down. You're all up and down quarks. There are 3 pairs of quarks, the up and down, which you are, the strange and the charm, and the top and bottom. The last 2 pairs don't stick around that long. But your protons and neutrons are made up of up and down quarks. Your proton has 2 up and 1 down, and your neutron has 2 down and 1 up. The up quark has a positive charge of 2/3. The down has a negative charge of -1/3. So 2 up and 1 down, plus 2/3, plus 2/3, -1/3, or 1 is a proton. 2 down and 1 up, -1/3, -1/3, plus 2/3, or 0, a neutron. But if you're all virtually all space. And the atoms on the floor are all space. Why don't you fall through the floor? Gravity is keeping you grounded, but why don't you keep on going? And gravity pulls you right down into the center of the Earth. What's holding you up? Well, maybe you're a magician, because you actually don't touch the floor. You levitate above the floor, 1 angstrom unit, 10 to the minus 10 meters. You don't touch anything. But what really is keeping you up? Then there must be a force stronger than the force of gravity trying to pull you down to keep you from falling through the Earth, or walking through the wall, or pressing your finger through your hand. Well, your atoms are surrounded by electrons which are negatively charged. The atoms in the floor are surrounded by electrons which are negatively charged. Like charges repel. So it's that repulsion, if you like, that's keeping you from falling through the floor, walking through the wall, or pushing anything through your arm. What's it called? Well, it's called the electromagnetic force. Let the force be with you. So maybe that explains certain things as well. Now, your your nucleus, then, except for hydrogen, has several protons. And the protons, as I mentioned, are all positive. Again, like charges, repel. So what's keeping you together? What's holding your atoms together? I know you've had days, for instance, when nothing seems to be going right. Whatever you do, it doesn't seem to matter. You can't seem to hold it together. Everything seems to be falling apart. Well, there you've got in the core of your atoms, you've got like charges which repel. So what's keeping you together? What's keeping your atoms together? There must be a force that's stronger than the electromagnetic force. What's this force called then? Which operates in the nucleus of your atoms? It's called the strong force. Let the force be with you. But if you're all mostly hydrogen atoms, how would you get that? Where did that come from? Well, before the 1920s, no one knew. Then Hubble, looking through the largest telescope on Earth at the time, at the Mount Wilson Observatory in Los Angeles, he saw that all the stars were moving away from the Earth, or receding away. What does that mean? What's the significance of that? Well, it means that space itself is expanding. Now, if a space then is expanding, it must have come from a smaller and smaller place. And extrapolating back in time, going back to when everything started, it turns out to be 13.8 billion years ago. And what does it mean to have time equal to zero? Science cannot tell you, and never will be able to tell you definitively. Everything, all the forces, we're talking about 3 forces already. Force of gravity, strong force, electromagnetic force. There is a 4th force, which we'll get to in a second. And everything else, it's all in the size of a golf ball, or less, a molecule. Now, another scientist called Planck, he said that time is discontinuous. What's that mean? Well, you can start off with 1 billion years and break it down to a million years, 100 years, a year, a month, a week, a day, an hour, a second, a microsecond, a nanosecond, until you get down to 10 to the minus 43 seconds. That's 0.00043 times. And you can divide it no further. He called it a quanta of time. Excuse me. We now call it a Planck time in his honor. So if you can't go beyond 1 Planck time, how are you ever going to get from 1 Planck time to time equals 0? So science, by its own theories, say they will never know. They can never find out. Unless they dispute Planck as one of the founders of quantum mechanics. Another thing in mathematics, when you divide by smaller and smaller entities, you get a larger and larger entity. For instance, if you divide by 1/4, you get something 4 times as big. Keep on dividing by a smaller and smaller number until you try to divide by 0, and all hell breaks loose. You get infinity. And you can't do much with infinity. You multiply infinity by 2 and you still get infinity. You add 4 to infinity, it's equal to infinity. So math really breaks down. They call it a singularity. So time equals 0 there also is a singularity. And does that mean there's something infinite then that creates the finite? Something with time starts? Something before that has no time? Well, again, science is at a loss to definitively explain how you and everybody else in the universe came into existence. They can speculate, of course, and have hypotheses. But for it to be a true theory or a true fact or a true law, you have to have empirical evidence, and you have to be able to even go back into a lab and test it out in a lab and have other scientists collaborate that as well in another lab. So they may have a hypothesis. First is this, they have no evidence, but they say it's possible there's multi-universes more than this particular universe. But so far they have not found any evidence to support that, only theoretical, but not a true theory. But science can't explain it, but many religions do. They say there's something with something infinite that creates the finite, and something that is all powerful, omnipotent. Because scientists say that between the first to second and time equals 0, first Planck time rather, and time equals 0, all the forces are together in a multi-force. Well, religion also says, as I say, something that is omnipotent, all powerful. But then at first Planck time, at 10 to the minus 43 seconds, the force of gravity separates from the superforce. 10 to the minus 35 seconds, the strong force separates from the superforce. And at that time also the universe expands, inflates at a rate faster than the speed of light. There's evidence for that. But if you think of inflation as when you blow up, for one thing is that the universe is very uniform at that time. And if you blow up a balloon and inflate a balloon, then the surface of the balloon is also very uniform. Right? The more you blow it up, the smoother it is. There's other evidence too. Now, what's this? Oh, I thought nothing can go faster than the speed of light. The speed of light is constant. You look at a planet coming towards you from the planet, and the light of the planet going away from you, and you'll measure the light at the same speed. It's 10 to the 10 centimeters per second. So how can anything go faster? Well, nothing goes through space faster than the speed of light, but space itself can expand faster than the speed of light. So 10 to the minus 12 then the electromagnetic force separates from the superforce. A lot of things happen in the first second. And also, the fourth force, the weak force. Now, you're in that room and maybe no one can see you, but you're a radiant person. You have radiance, maybe they should be noticing you. But you're not all that radiant, to be truthful. It'll take several million years times the age of the universe for you to radiate away, for you atoms to radiate through radioactive decay caused by the weak force. The weak force is nevertheless important for you. Without it, you would probably die. It keeps the center of the Earth, which is iron, molten. And as the Earth turns on its axis every day, it sets up an electromagnetic field or shield around the Earth that protects you from harmful solar radiation and harmful cosmic radiation. And too much of that is not good for you. It also protects the atmosphere from being blown away by the solar radiation. And the atmosphere is good for you too because you breathe the oxygen. It also mitigates at least things from falling out of the space and hitting you, causing a lot of consternation. It usually burns them up in the atmosphere, or at least makes them small enough that they're not going to really harm you that much. It does let a few big asteroids through, and we'll talk about that later, but very rare. Let the force be with you. At that time as well, it's where you get all your particles and antiparticles. That's not just fiction. For every particle, there's an equal and oppositely charged antiparticle. But the thing is, when the particle and antiparticle come together, they annihilate each other. They change from matter into energy. Now, before 1905, everybody thought, no, matter and energy, they're two different things. There's a conservation of matter, there's a conservation of energy. But Einstein came along and said, no, you were all wrong. They're exactly the same. They're equal. E equals mc squared. Your energy is equal to your mass, that's the amount of material you have, times the speed of light times the speed of light. His special theory of relativity. So scientists, even though they have the consensus of opinion, was before that, and everybody else, that they're two different things. So even scientists, and majority of scientists, can be wrong. So when you have a theory that disproves the previous theory, you have to discard it, or say that you use it only under certain circumstances, or incorporate that new piece of evidence in your new theory or new fact. Then at 10 to the minus 1, that's 1/10 of a second, is where you get your protons. But then at 1 second, something happens very significant, which again science can't understand. But for every billion antiparticles, you get 1,000,000,001 particle. Some say 100 million instead of 1,000,000,000. And if that didn't happen, and if you wouldn't be around, because you can't be made. You can't have any antiparticles, because if you have any antiparticles, well, they would combine with your particles, and you blow up into energy and everything else. So that phenomenon at 1 second, if that didn't occur, then nothing. You wouldn't be here. And so they try to take it back to the lab and see what's going on. They try to change energy into matter, but they always get the equal amount of particles and antiparticles. So they're not really sure why that happened. So not only is there a mystery about the time equals zero, there's a mystery of time equal 1 second. But everything is so hot and dense that nothing can come together. You've got your protons, you've got photons, which are particles of light, electrons, all in, if you like, a plasma. And about 308,000 years, I think that's the number of years, I looked that up, I may have forgotten, after it cools enough so that the proton can capture an electron. And what's that? One proton, one electron. Hydrogen. So that's where you get all your hydrogen from. And you thought you were under 100 years old. Well, most of your atoms at least, are 13.8 billion minus 308,000 years. And excuse me, that's why you got all your hydrogen in your body. Now, this theory, and I think there's enough evidence to recall it almost like a true theory, or a law, or a fact. It's called the Big Bang Theory. But did you know, the person that named it did not believe in this theory. He thought of it was he had a steady state theory of how the universe works. For every star that is created, there's an equal star that disappears. Same as Hoyle, according to Hoyle. But with this new evidence, then his theory, or his hypothesis, is not followed now. And everyone believes in the Big Bang Theory. So the Big Bang Theory was named by someone who didn't believe in the Big Bang Theory. Nevertheless, Hoyle, who was a very famous scientist in Britain, he showed how you could thank your lucky stars that you got your other atoms, if not your hydrogen. So just because he's wrong in one aspect doesn't mean that everything that he produced was wrong. Excuse me. But what's the evidence then? Well, how did Hubble know, for instance, that the stars were going away from the Earth? Well, light is both a proton, is both a photon, or it's both and a wave. It's both a particle and a wave. Hold your two fingers up close together and look through it with one eye, and you'll see faint lines in between your two fingers. They're called interference lines, where the waves of light are interfering with each other. Like when you throw two rocks in a pool, the waves interfere with each other. And back in the 1600s, Newton said that you pass the light through a prism and you get the colors of the rainbow, or you get the electromagnetic colors. And the color, the red, it has a larger wavelength, the distance between the two crests, than the indigo at the other end of the spectrum. It has a shorter wavelength. So consider a piece length, and the wave goes up and down. So if the wavelength is larger, it can only go up and down less than if the wavelength is shorter. So the frequency of red light is less than the frequency of indigo. Sound also is propagated by waves. You hear a train coming towards you, the train is pushing the waves together or squashing them. So the wavelength is shorter, and the frequency is higher, the pitch is higher. As the train goes by, it stretches out the waves, so the wave length is longer, and the frequency is less. So you hear the train going from a high pitch or high frequency to a low pitch, a low frequency. Same for light. So when light is going away from you, it goes from a high frequency to a low frequency. It goes from indigo to red. It's called a redshift. So looking through a spectroscope, and you can see the different signatures of the different colors, you can see that the stars are shifting towards the color. The light is shifting towards the red. Therefore, the stars and the light is going away from the Earth. But what about all these particles, quarks? Well, there is something that the instrument that they call it the Large Hadron Collider in CERN, and one of them, the most powerful, in Switzerland. It's the most intricate piece of equipment ever built. It's a 27 or so, I'm not sure, miles or kilometers, underground, with a magnetic hydroelectric electromagnetic compass. Accelerate particles such as protons. Hadron is anything with mass, by the way. And in one direction, and then the same particles in the other direction, and smash them together. See what they're made of. Like a car roller derby, they smash them together and the parts fly off to see what they're made of. At first, there were so many particles, they called it a particle zoo. But now they've got a particle theory, which explains everything you might want to know about everything. How everything is made up. There are the three pairs of quarks, the up and down, which you are, the charm and the strange, and the top and the bottom. And for each one of those quarks, there's a lepton. For the up and down, the lepton is the electron. For the other two pairs of quarks, it's the tau and the mu. And then there's the four forces, which I mentioned, the electromagnetic, the gravity, strong force, and weak force. And for each of those forces, there's a particle called a boson. And those bosons, is the interaction of those bosons is what gives the force, creates the force. For instance, the electromagnetic force, the boson is light, or a photon. So you try, try to hold two magnets together, and two north poles or two south poles, and they resist. They don't want to come together. What's stopping them? These photons of light being exchanged between the two south poles or two north poles. Boson for the strong force is the gluon. A boson for the weak force, there's two, W and Z, not Z, but Z. And the boson for the force of gravity is the graviton. But they couldn't find the graviton. They probably need a collider the size of the solar system. So they just found, just recently, the last 10, 20 years, another piece of equipment that they've used to find, to discover gravity waves, or gravitational waves. It's LIGO, L-I-G-O, standing for something. And it used interference, it used waves. And now, whenever then a theory predicts something, and it comes true, then it needs more credence to that theory. So they assumed there should be a graviton, and when they found the gravitational waves, then there must be a graviton too. But there's a guy called Higgs thought there should be one more boson. It gives the other particles mass. So he predicted that back in the mid 20th century, and it was until 2012 that they found this particle, and they call it a Higgs particle. And of course, all the particle physicists jumped up and down because, again, it gave their theory more credence. So that does give some credibility to the Big Bang Theory. The other thing that happens at 308,000 years after the Big Bang is that photons of light can escape. Before that was all dark, right? And we're still getting hit by those photons of light. We call it the cosmological background radiation. And 3% of your static that you get in your AM radio and 3% of the static on an old TV with your aerial is that light. It's now microwaves. It's cooled down quite a bit. It's only 3 degrees above absolute zero being minus 273 degrees centigrade. So it's about 270 degrees. So that's another reason why we support the Big Bang Theory. So we're talking about then how you got your hydrogen, but you have other atoms too, right? And I say you can thank your lucky stars for that. Because Higgs. So Doyle was the first person to explain how that happened. What happens then if you get all this hydrogen? It becomes bigger and bigger, denser and denser after the first half billion to billion years. Then it becomes so hot in the center, and the force of gravity, and this is my hypothesis at least, overcomes the force of gravity. So the space between the circumference of the atom and the nucleus of the atom disappears. And the two protons within the hydrogen atoms fuse together. The process is called fusion, and it creates helium atoms with two neutrons, two protons, and two electrons. But it also gives off a lot of other extra energy, like in a bomb, a hydrogen bomb. So you've got the fusion process exploding, expanding, and you've got the force of gravity pulling everything, attracting everything together. That take a war between the two. And in the process, you also have all this heat and light and energy being given off. What do you got? Could say Judy Garland. But in any case, a star is born. What's the nearest star to the Earth? You should know its name, actually. You probably do know its name. The name? It's the Sun. So the Sun is a star converting hydrogen into helium and giving off energy in a form of warmth and light. Now, a star which is over 8 times more massive than our Sun, when it uses up all the hydrogen to create helium, then it fuses the helium together to create ever so much more heavier the elements as you go up the periodic table. The periodic table is a table sorting out all the elements, starting from the lightest up to the heaviest. In other words, as you go up, there's more protons and more neutrons as you go up the table. But when they get to iron, it doesn't give off energy when it tries to fuse them together. It requires extra energy. So remember, there's a tug of war between the force of fusion and the gravity force. So there's nothing opposing gravity now, and the star collapses instantaneously on itself, and with such force it blows up, which is what we call a supernova. And the supernova has so much energy, it creates more light, for instance, than all the other stars in the galaxy. Some 100 billion to 200 billion stars. So there's enough energy there to fuse together the iron plus most of the heavier elements in the periodic table. But it leaves behind a core. A core with all that, the mass, all the protons with no space. Very dense. It's called a neutron star. Take a teaspoon of that, it would weigh or be as massive as all the cars in North America. Now I tried that, and but then if you take a teaspoon of that, and remember that your electromagnetic force usually doesn't let you touch anything or anything touch you. But in this case, the force of gravity was so great because it was so dense and so massive. It went right through my hand and right down into the earth. And to be truthful, I gave up counting, measuring the mass of all the cars. I mean, maybe 2 or 3 was the most. So, what happens to all that material then that is spewing out into space? That created in the star and that from the supernova? Well, gravity takes over again and combines it and forms a second generation star. Our star formed some 4.6 billion years ago. It's a third or fourth generation star. So, where did you get all your other components, physical components, your other atoms? Spread over 13 billion years ago. Comparing to 500 million years after the Big Bang, down to 4.6 billion years ago, when the solar system was created. So you could have a carbon atom in one finger that's 12 billion years old. Carbon atom in a different finger, from a different solar system in a different galaxy, that's 6 billion years old. So there are a lot of events that happen for you to get here, and how you got here, in terms of your physical components. Many of which science cannot fully understand. There's an astronomical number of events, both literally and figuratively, as to how you got here and what you mean. But you still aren't living. You just have your physical makeup. But of course, all those atoms have to come together to form a you, and something that can talk and walk and propose very significant ideas. So when the solar system started, there was a lot of material floating around, bashing into each other. The Earth, the Sun, formed by the lighter elements, hydrogen, and maybe some helium. Everything else that sort of swirled around the Sun. Small particles like dust, they would, electrostatic charge would brought them together. And then when the bigger force of gravity would have brought them together. It was so chaotic, everything was swirling around, bashing into each other, breaking up, and gravity was again bringing together the bigger things until you got and created your planets, probably 100 planets, and several dwarf planets. Probably more dwarf planets now they figure than there are planets. Pluto was just demoted to a dwarf planet. And the planets were hitting each other and demolishing each other. One planet, probably the size of Mars, called Theia, hit the Earth at such an angle, 45 degrees, that it didn't demolish it or it didn't bounce off, but it took a big chunk of the Earth's crust and spewed it into space, which went around the Earth. And gravity brought that together to form our moon. So our moon is part of the Earth, came from the Earth. How do we know that? Next time you take a trip around the moon, note, there's just the one big black spot, right? Whereas this spot, this side, there's lots of them, the lava lakes. And why is that? That's because the crust on the other side of the moon is some, and again I can't figure the exact figure, but it's some 25 kilometers thicker than the crust on this side. That allows the lava to come up in the cracks and form more lava lakes on this side of the moon. That's why you get the man in the moon. And if you think that's sexist, you can take a look at the moon from the top to the bottom. You'll see a man and a female kissing each other. So that's maybe why it's so romantic. And the reason why that is because the Earth was so molten at the time, and the moon was so close. Tidal waves would have been a mile high. And the material going around the Earth, the moon itself would be on the other side. The moon was much cooler, and more material would settle on that side, making the crust thicker on the other side. Also, the astronauts brought back rocks which they think could only be created on Earth. So the moon is important for you. It stabilizes the moon, the Earth. And many think that complex life like you could not survive without the moon. Life itself. When did you get your life? Science does not have a definitive answer for that either. They have some hypotheses. But they try to create life in the lab, and it doesn't work. It doesn't happen. The closest they can come is to get amino acids, which are some of the foundation for life. They have some hypotheses, of course. Oh, well, there was one scientist that did create life. But really, he didn't create it from nothing. No, he created it from other parts of things that were living one time but now dead. Took them and sewed them all together and added a little bit of lightning and brought it alive. Science doesn't want to talk about that because it didn't turn out that well. He created a monster, went around and terrorized everyone. It's not they don't really give the secret away of how they come up with all these magic potions, all these drugs. It's like the witches in Macbeth, where they have their cauldrons, mixing them up, adding isonewts and so on. They don't really want to. It gives them a bad reputation. But for those of you who are not on this planet, I've been talking about science fiction, not science. So no, and his name, by the way, was Frankenstein. But no, they have not created life, and they have not seen it happen. They can give some ideas. But in order for it to be a true theory, you have to have empirical evidence or observation, not just speculation or hypothesis. And then, as I say, take it back and prove it in the lab, which they're not able to do so far. Yes. So life as we know it, at least came up from the oceans onto the Earth. But it started off as like a one cell, very boring, and it would split into two. Life is defined as anything that can create itself, right? It can replicate itself. And then the number of cells would cooperate with each other into a multi-celled organism, and so on. Well, when did you first, I'm sorry to be somewhat personal here, but when did you first have sex? What kind of sex that I'm talking about? Okay. Well, it was only half a billion years ago. And you, as an animal, there are plants and animals, and there's sort of a symbiotic relationship between the two. Plants breathe in oxygen and give off carbon dioxide. Did I say that wrong? Yes, I did. Plants breathe in carbon dioxide and give off oxygen. Animals breathe in oxygen and give off carbon dioxide. And plants grow, a process called photosynthesis, where they take energy from the sun and to produce their sugars. Animals, such as you, well, you get half your genes from your biological mother, half from your biological father, and your genes are composed of cells. And your cells at the center have the core is called, they have the deoxyribonucleic acid, DNA. And that DNA defines your physical characteristics. Color of your hair, color of your nose, size of your nose, the color of your eyes, how tall you can get, how big you can get, and everything else. So physically, you're made up of your DNA from your mother and your father. And what happens when you grow? Your DNA is like a ladder with rungs in between. There's 4 different chemicals. And when you grow, the ladder splits down the middle, and it's twisted, so it's called a double helix. And then the left side, new left side or new right side comes together and matches totally, equally, with each other. Billions and billions and billions and billions and billions of times, except when it doesn't. Sometimes you may get clunked by solar cosmic radiation or something, and you change some of your DNA on one of the rungs or one of the sides. And since your DNA defines your characteristics, then you could pass on your DNA to your offspring, and it's modified, and therefore their physical characteristics could be modified as well. That process, of course, is called mutation. We'll talk a bit more about that later. So you have all these animals and plants, except there's one. There's animals at the bottom of the ocean that were discovered, well, a few decades ago. And there's no light down there, so there's no plants. Too dark. So they must have come about by a process, a chemical process from the chemicals being spewed out in the volcanoes underneath in the bottom of the ocean. So again, that's something that really can't definitively describe how that happened. They can certainly speculate, and how else could it happen other than that? But there's always a smartass in every crowd. And there was one smartass plant. He wanted to hog a little more of that precious sunlight. So he grew higher than the ground-based plants. And most of the other plants, when they die, they give off back the carbon dioxide into the atmosphere to compensate for that which they used when they were living. But this particular plant didn't rot right away. It took millions of years before there was something there, termites for instance, that would rot, to help them rot. It just lay down and eventually turned into coal. And this plant we now call a tree. So the atmosphere back then would have been the more oxygen than there is now, because the trees didn't get back carbon dioxide. So insects which are around then would be much larger because they breathe through tubes. And if there's more oxygen, the tubes can be bigger, and so they can still get enough oxygen without being absorbed in the tubes. So centipede would have been the size of a crocodile, for instance. But you're damn lucky. Yes, a number of close calls for you to be here. Life itself, and you had a number of close calls. You look at the geological age of the Earth, and there, between the Jurassic, the Triassic, Cambrian, and so on, a lot of catastrophic activities, a lot of catastrophes that almost wiped you out. 225 years ago, one of 5 major ones, wiped out 70% of all living things, 90% in the ocean and the rest on Earth. They figure that all that coal that was laying around in Siberia caught fire, and that's what happened, and wiped out most of the life on Earth and in the ocean. Then, of course, you had the age of the dinosaurs came up. 160 million years they ruled the Earth. And during that time, the continents were all one, called Pangea. Then they split up into the continents we now see, and are still moving, but so slow we don't recognize it. So who thought of that? How did we know that? Well, you can look at yourself. You can see that South America and Africa sort of fit together like pieces of the jigsaw puzzle. Plus some of the other continents too. But that's just a hypothesis, or what kind of evidence do we have? Well, actually, a guy called Wagner, he obtained that evidence. First of all, he speculated or saw that the continents seemed to stick together, or to come together like pieces of a jigsaw puzzle. Then he looked at fossils of plants and animals on this side of the Atlantic, and how they matched up with fossils of plants and animals on the other side of the Atlantic, and nowhere else in those continents or any other continent, indicating they must have all started in that same place. Then he looked at land formations, and they started at one side of the Atlantic and continued on the other. And even sedimentary rock, which lays down at the rock, and in particular layers. And he found layers on the sedimentary rock on the other side of the Atlantic that matched up perfectly. Okay, and there was a split at that point. Fourthly, he looked at fossils in the north, and found that they could only have lived in the south. So the land itself must have moved from the south to the north. So that was evidence of the split of the Pangea into several different continents. So is he heralded as the greatest geologist or greatest scientist at the time? Far from it. He was vilified. He was made the laughing stock of the geological and scientific community. They thought that's preposterous. They didn't even bother looking at the evidence. But just dismissed it. So here again, all current thoughts of all the leading scientists can be wrong. You should follow the evidence, no matter where it leads, not the opinion or the consensus, even the consensus of opinion of scientists, unless there's evidence to support that opinion. Wagner died trying to accumulate more evidence in Greenland, helping out some people stranded in the snow, walked off, never to be seen again, and now to know that his theory, and you can call it a theory because there's evidence to support it, and his health would be vindicated. It remained for another couple of decades, but none of scientists explained how that could happen. The continents ride on plates and on top of the magma, and that's how they move around. And where the plates meet, you get a lot of volcanic activity and earthquakes. It also explains how mountains like the Himalayas were formed when Africa separated, India separated from Africa and bashed into Eurasia to form the Himalayan mountains. So this happened during the age of the dinosaurs. The age of the dinosaurs, as I said, lasted to 160 million years, to 65 million years ago. And then there was another catastrophe that wiped out the dinosaurs and some of the larger, other animals. Jupiter, which is larger, more massive than all the other planets combined, and often attracts through gravity a lot of the meteors, comets, asteroids that may come down to hit the Earth. But it let through a whopper, and the whopper even got through the Earth's atmosphere 65 million years ago and landed in the Yucatan Peninsula in Mexico. Caused quite a stir. All that energy from the collision burnt off a lot of the vegetation and spewed off a lot of the Earth into the atmosphere, circled the Earth, and cut off the sun. So it became dark. And dinosaurs require heat because they're cold-blooded. They're reptiles. So they died off. And you, as a mammal, previously you had to stay underground in the daytime so not to be eaten up by the dinosaurs. But when the dinosaurs became extinct, came out and be able to live in the daylight, or eat in the daylight, and proliferated and took over all of the niches, if you like, of the dinosaurs used to occupy. So, although it wasn't that good for the dinosaurs, it was probably good for you. Now another event 10 million years ago is very important for you as well. North America and South America came together. Before that, there were two separate continents. That changed the ocean currents and changed the climate of Africa. So it could no longer support the number of trees that it did before. It had a lot of grassland. And some of the animals said, it's kind of crowded up here. I think I'll try my luck on the grassland. And probably some cosmic radiation hit some of their DNA, modified, at least for their offspring, the characteristics, and those that had the right, had the characteristics that made them better to survive on the grassland, able to live and pass on their DNA to their offspring, and so on, and the rest is history. So you are here because of all these different events, many of which science cannot fully understand. And it's astronomical, literally and virtually, how many events happen. And for instance, your mother and father had to meet and produce you, and so you are 1/4 physically of your from the DNA from your mother and DNA from your father. And their mother and father had to meet and produce them. And over the million years, there'd be 16,000 different events that have to. You're part of 16,000 other people, physically. I think that's the right. You'd have to work it out. Let's say there's 4 generations in each 100 years. And then you're on a planet that is just the right distance from the sun. And as far as we know, the only planet that has life. It's not too cold and not too hot. The water that you need is not frozen or doesn't evaporate. Right distance, the Goldilocks position. So now trying to find other planets, because they now know that other stars have planets, sometimes several planets. So they have satellites that try to detect these planets and see if there's any life. Probably a telltale sign would be if there's any oxygen in the atmosphere or any water vapor. Now this has gone on for at least, from Earth at least, through telescopes, for some time, in search, even for intelligence life. Search for extraterrestrial intelligence, SETI. A scientist that was instrumental in that was Carl Sagan. He was a leading scientist, and he wrote a documentary called Cosmos. It explains a lot of how you got it. He called you Stardust. You made up of Stardust. And not to quibble, but all of you except hydrogen is Stardust. He also called the Earth the pale blue dot. Because if you look from outer space, you see this vast blackness and one little blue dot. It was just the Earth blue because it's got so much water. And all that ever happened, everything, is on that one little pale blue dot that we know about. And it's like an organism. And if one part of the organism isn't working properly, it affects the whole organism. So there's the plea then to stop your wars and get along with each other. Otherwise you might destroy all of Earth, all the organisms. Another scientist now that has a new series of Cosmos, more than 10 episodes. He's knowledgeable about a lot of scientific phenomena. Neil deGrasse Tyson. He was inspired by Carl Sagan, that's why he becomes scientist. So, but they also now think that there could be life in the solar system. They're finding that there's a lot more going on moons than we thought about before. Some moons, I think it's Io, have volcanoes giving water out, so there must have been water underneath the crust of the planet. I think I got the plot right. I'm not sure. I have the moon right. So there's a lot of things going on the planets, and particularly on the moons, and on some of the dwarf planets. As I say, they think there's more dwarf planets now than there are planets. Dwarf planets mainly belong beyond Pluto, which has been demoted, if you like, to a dwarf planet. And there's one actually in the asteroid belt called Sirius, I think. And they seem to have a water. and the water can be ice, and then underneath the crust there would be water because the tides from the force of gravity of the other tidal forces caused by their planet would keep the water, the keep it in liquid form. Now, of course, even Mars might have had life at one time, and they now have a satellite landed on it. I think it's called Perseverance. It's going to dig up, and it just successfully landed just a few weeks ago. They're going to dig up samples of the Earth, of the Mars, and talk about a future a mission to Mars can bring it back and analyze it, see if there's any dead or living microorganisms. But so far, at least, the only life we know of is here on Earth. And that is there within the solar system, which has is it 7 or 8 planets now? And the solar system is one of 100 billion to 200 billion stars, or solar systems, within this galaxy, the Milky Way galaxy. And the Milky Galaxy has over 200 billion galaxies in the universe. So where are you located? You only occupy a very small part of the universe. And of course, you got all your atoms other than hydrogen spread out over 13 billion years. It's only 9 billion because you have to subtract off 4.5. Did I say 13 before? Yeah, 9 billion years. Well, a multitude of different stars and different solar systems and different galaxies. And then you've got your hydrogen, 380,000 years after the Big Bang. Then you got your particles 1 second after the Big Bang. And then, of course, you got all your forces within the first second. So, as I say, an astronomical amount of events had to happen for you to get here, and how you got here, and where you are. Now, some of your characteristics then, for instance, how big you can become, or how massive you are. Well, what do you weigh? Well, before the 1600s, people didn't really know too much about your weight. Now, again, in that room, maybe people don't really notice you or can't be heard, but you are attractive. You're an attractive person. You may not think so. You say, well, maybe from farther away, I might not look that bad, but when I get closer, you'll see I'm maybe grossly overweight. I'm too fat. Contrary. The closer you are, and the bigger and fatter you are, the more attractive you are. Newton, back in the 1600s, saw an apple fall to the ground. He said there's an attraction between that apple and the earth. He came up with a formula which applies for any two objects. He said it's proportional, or if you like, equal, to the mass of the apple, amount of material of the apple, times the mass of the earth, divided by the distance between the center of gravity of the apple and the center of gravity of the Earth, squared. So you're in that room, then their attraction between you and the other people is equal to their mass times your mass divided by the distance between the two of you squared. Because this formula applies for any two objects, not just the Earth and you. But again, you're not all that attractive because you're not massive enough, or your friends aren't massive. So you'd have to go outside. Maybe you'd be more attractive with it to a mountain, or a mountain would be more attractive to you. But you'd be very attractive to the Earth itself. Now, to find out the amount of attraction, take some instrument, slide it between you and the Earth, and see how much it's depressed. We call that a scale, and we call what you read is your weight. So your weight is equal to your mass times the mass of the Earth divided by the distance between you and the center of the Earth squared. And by the way, the force that Newton was defining was the force of gravity. F equal Rg times m1 m2 minus r2 squared. So you want to lose weight, go climb a mountain. The distance there is greater to the center of the Earth, therefore you should weigh less. Oh, you want to gain weight, go down into a mine. The distance there between you and the center of the Earth is less. So you weigh more because you divide by the distance by square. Again, not so much. Or go to the want to lose weight, go to the equator. The Earth is not a perfect sphere; it bulges a bit at the equator. Or if you want to gain weight, go to the North Pole, South Pole. Again, I don't think you can measure it; it's probably not good. But if you want to really lose weight, go to the moon. It's only 1.2% as massive as the Earth. And so you'd only weigh, I believe it's 1/6, if I remember right, as much on the moon as you do on the Earth. Even though you'd have to compensate because the distance is much less. But still, you'd only weigh a fraction of what you do on Earth. And so if you want to break some Olympic records, I suggest you go to the moon. Try your high jump there and see how far you go. Or your pole vault. When you saw Armstrong walking around the moon, he was almost hopping even though he had heavy equipment on his back. And that's why he didn't weigh as much. The other thing that your DNA describes would be your height, how high you can come. Now there are other nutritional things too, and that's why some years ago, you'd find North Americans were taller on average than many of the other countries. Now not so much. But their limitations would be from your DNA. Now it's probably, some would say, advantageous to be somewhat taller, more like tall, dark and handsome. And if you're a tennis player like Eisner, he's almost 7 feet tall, so I think 6'10" or something like that. Get better leverage and he can serve much faster. He's got the fastest serve. Another one would be Bronick. He's only 6'5", but still, the taller you are, the more potential you have to serve faster. But supposing you want to be more normal, quote normal, you want to appear to be less tall. Well, you measure yourself then, and if you're 2 meters tall, say you measure yourself in kilometers, and you're only 1/2000th of a kilometer. Or measure yourself the distance from across to the center of the Earth. I think it's 4,000 miles is the unit of length. or the distance to the moon. Now the moon is several thousand kilometers away. Or the distance to the sun, millions of miles. Now when you get to the large distances like that, you use the speed of light to define the measurement. So you use the distance that time travels. For instance, it takes 1.2 seconds or so for light to travel, or any part of the electromagnetic radiation, for instance radio waves, to travel from the moon to the Earth. This is why when Armstrong answered Houston, it took 1.2 seconds for him to receive the message, and another 1.2 seconds for him to answer it. So there was a delay in the response of up to 3 seconds. So we call that the distance then 1.2 light seconds. And the light from the sun takes 8 or 9 minutes to arrive. So that distance we say is 8 or 9 light minutes away. The distance to the some of the other planets would be like months away, like years away. Distance to the stars, thousands of light years, millions of light years, billions of light years. The farthest away star that saw through the Hubble telescope is 13 billion light years away. The light takes like 13 billion years for it to come reach you. Now, if you're shorter and you want to appear to be, quote, normal, although there's an advantage for some people to be shorter, jockeys and gymnasts and so on. But if you want to appear to be taller, then you measure yourself in smaller units. If you're a meter tall, then say you're 100 centimeters tall, or 1,000 millimeters tall, or 1.6 times 10 to the 35 Planck times. Planck lengths away. The Planck is the Planck time is the time it takes a light to travel 1 Planck length. So it's very small. So both time and space are have the smallest units. So if you're in that room and you want to maybe talk to someone and find out how they are, you can never really tell them how they are at that time, how they are now. You only can see them as they were billions and billions and trillions of Planck times ago. The time the light takes to arrive to you. You never see them as they are now. So you want to look in the past, you want to time travel. All you have to do really is go outside and look up in the sky. Because you'll see things as they were when the light left the stars, for instance, which could be millions of years ago. So you're looking into the past, you're time traveling. So you can travel and then into the past by just observing what's happened in the past. You can also travel into the future. Now, I gave you maybe a wrong impression when I said, oh, you're a radiant person or you're an attractive person. What happens really, rather than an attraction between you and someone else, you fall for them or they fall for you. You create a space around you, you change the space around you, or the other person changes the space around them, and you fall into that space. Like when you stand on a trampoline, you form a wall around you and put a basketball on it, it'll fall towards you, right? Well, you go around changing your space around you. What's this? Are you crazy? Space just must be the same everywhere, isn't it? How can you change space? Well, Einstein back in 1915 says that gravity, it's not what Newton said, it's not the attraction between two objects divided by the distance between them, squared. It's a warp in space-time. He came up with that idea with a thought experiment. People, the consensus of opinion was that that's kind of weird, like we think now. But to get an idea of what he's driving at, here's another thought experiment. Take a rubber sheet representing space-time. Let's leave out time for the moment to say representing space. And take two ball bearings, one larger than the other. Place the larger one on the rubber sheet, and it forms a imitation. The larger ball bearing would represent the Earth, and the smaller one would represent the Moon. Then you roll the smaller ball bearing representing the Moon towards the larger ball bearing representing the Earth, and the Earth has formed a warp around it. The ball bearing has formed a indentation or well around it, and depending on the mass of the two objects, how big they both are, how fast you roll the ball bearing, the smaller ball bearing, and how close it comes to the larger ball bearing, where the Moon comes to the Earth. It'll either go right by, or it'll hit the warp caused by the mass of the Earth and be deflected, or the indentation of what the larger ball bearing forms in the rubber sheet, and it'll either be deflected and keep on going, or it'll hit the warp and go around it, or the smaller ball bearing will hit the ball and go around the other ball bearing. Not because there's an attraction between the ball bearing and the other larger ball bearing, or the Moon or the Earth, but because the space around the Earth has changed. It's been warped by the mass of the Earth. Now, there was a consensus of opinion, and a lot of journalists said, nah, that's pure hogwash. And what did Newton say? I don't care how many people say it's wrong and have their opinion. Give me one scientist or one person with one piece of evidence that contradicts it. It's the evidence that has to be prove us wrong, not your opinions. Thank you very much. And when the evidence came, they brought brought it back to Earth not Earth really, but to do an experiment. The experiment they used, the tool they used was the solar system. They waited till a solar eclipse and looked at the stars behind the solar eclipse and found that they had displaced. In other words, the photons going around the Earth were deflected because of the space around the Earth was warped. Around the sun was warped, and the stars appeared in a different location. Now, of course, this is the sun I'm talking about, not the Earth. And Newton became famous. Now, what about space and time? Well, time as well has changed. You go around changing time. But again, you don't notice it because you're not that massive. But if you go towards a large mass, time slows down. So gravity is a warp in space and time. Now, you don't really notice the time being different because you're located within the same warp, location within the warp that the Earth, the mass of the Earth forms. And you can also use Newton's laws to describe a lot of different common day practical experience. But you can't quite definitively define the orbit of Mercury around the Sun unless you use Einstein's. So here's a case then that although Newton's theory is, they could say, is correct, Einstein's is at least closer to the truth. You can often get away with just using Newton's laws. And again, time for most people, it would be very, very low. Mass is different. Mass, how close you are to a particular mass would change. You wouldn't notice it, except if you want to go on a trip. You want to use your GPS to find out where you're located. If you don't incorporate Einstein's general theory of relativity, your GPS would be out in 2 hours because it uses satellites. And time on the satellite runs faster than time on Earth. You need a atomic clock to measure it. But if you don't incorporate that, your GPS would be out in 2 hours. So really, Einstein has defined how the world works, how the universe works, where there's mass. It's a world theory. Einsteinian world theory. Describing how things work in the universe. Was he given a Nobel Prize? Well, yes, but not for that. For his contribution to another theory. Both theories you can call true theories because they have facts to back them up. They're called quantum, the quantum world. His work with photoelectric effect, that when light hits an atom, it gives off an electron. And you can thank him next time you go to an elevator and it doesn't close on you, or the car doesn't close on the garage door. He didn't like the other world theory, and he was trying to spend the most of his career trying to combine the two theories for the theory of everything, incorporate the quantum world with the world with mass. Because in the quantum world, the masses are so small. It's at the other end of the spectrum. Everything is very, so small. And the force of gravity is so weak, you can mostly ignore force of gravity, except when you can't. And that's when something is small and massive, like a black hole, or at the beginning of the universe. And he didn't like it because it relies on probabilities. So in his theories, of course, everything is deterministic and by mathematical equations. Whereas in quantum world, or quantum mechanics, it's probabilities. And you have to sort of add up your probabilities before you get anything that approaches reality as we know it in the world with masses. where mass is important. And if you think Einstein's word is a little bit weird, where you go around changing your mass and you go around changing your space and time, what do you hear about quantum world? Quantum mechanics are now quantum field theory. The founders of that would be Planck, who said that time and space is discontinuous. There's the smallest unit of time, the smallest unit of length. And that everything is realized on probabilities. And anything, you have to determine, add up the probabilities before you can find out what really happens. Heisenberg, another founder, said that if two things are related, and then the more you know about one, the less you'll know about the other. For instance, if you want to know the speed and the location of a particle, the more you know about the speed, the less you can find out about the location, and vice versa. Not because you can't measure it, it's because that is reality at the quantum level. To show the weirdness, the standard classic experiment is a double slit experiment. You pass light through whatever with two slits, cardboard, whatever, and see what happens on the wall on the other side. You expect to get maybe two different lines. No, you get several different lines. Because light going through the two slits as a wave interferes with each other and forms the interference lines. As I say, like you get when you look through your two fingers and you see faint lines in between them, or when you get throw two rocks in, the waves interfere with each other, and you get several lines in the case of light. That's weird enough in itself. But look at the light before it goes through. Observe it. And you don't get several lines, you only get two, indicating it's changed from a wave to a particle. It's gone through a straight line. Why? If you look at it, does it change? It's kind of weird. And science really doesn't understand. Maybe you need, again, religion to help you out. There's something everywhere, changes that's needed to observe, you and everybody else, for it to exist. But then, okay, just release one photon at a time. So it has to either go through the left slit or it has to go through the right slit. Therefore, it should be just one line on the left, another line on the right. No. There's interference lines, several lines, indicating the particle must have interfered with itself. It must have gone through the two holes at the same two slits at the same time. How could that be? Well, it can. It is. Okay, look at the each particle then as it goes through. And then, lo and behold, you get interference lines. The particle has interfered with itself. Now, one of the co-founders of quantum mechanics, I forget his name, but he said he made working with the mathematics and quantum mechanics easier. He said anyone that thinks they understand quantum mechanics doesn't understand quantum mechanics. And yet, you can use it even if you don't really know what's going on, and it's one of the most accurate tools the science has. And there's nothing ever came along to prove any of it incorrect. what goes things out to 23 decimal places, etc. So here you have two theories of the universe, how things came about, how you came about, that are incompatible. One is continuous, the other is discontinuous. It's based on that. One is deterministic, the other is based on probabilities. One has certainty, the other has uncertainty. So does science really understand everything, the fundamental questions? Well, like, how can it? It has two different theories. It uses both of them as tools, of course. And they both are great theories. There's no evidence to dispute them. You can't explain why you have to have two different, one at the large level with masses and one at the quantum level without masses. The only problem is that, again, if you have at the quantum level, if you have large masses, you have small masses that are that are heavy masses that are small. Now, there's been other people that are trying to come up with a theory of everything. They use something called string theory. They really shouldn't call it theory because there's no real empirical evidence. They say that everything is composed of strings, and strings are millions and billions of times smaller than quarks. Even the forces are strings. The only problem is how you ever go to measure something that's small and bring it back into a lab and prove it, and you require 10 dimensions instead of 3. And so far no one's gone into a dimension and come back and talked about it. So it's quite theoretical as opposed to being a true theory or fact or law. Nevertheless, it's the particle sciences, or theoretical sciences working on that. The other thing that science then can't really understand why are all the constants and forces exactly as they are? Because if some of them were slightly changed, you wouldn't be here. The force of gravity, for instance, if it were slightly less, it wouldn't have brought together all the hydrogen, and the universe would be just totally hydrogen. It wouldn't brought together to form stars, galaxies, and you. Or if it were stronger, once the hydrogen was produced, it would have attracted it back into a big crunch. What they really have trouble with is the astronomical constant. Einstein put it in his theory of general relativity. We can call it lambda. And it would explain why the universe can expand or contract. He took it out because he, like everybody else, thought, well, the universe doesn't expand or contract. It just is. It's always been there and always will be. It doesn't change. Steady state, steady as she goes. But the big mistake was thinking that it was a mistake because you now need it to explain the expansion of the universe. So they look at, say, well, let's look and see how much it is. Let's measure it. Let's hypothesize and theorize how much it should be. And then let's measure and see how much it really is. And they're out by 10 to the 120th, the largest ever discrepancy. If it were what they theorized it should be, everything, including your molecules, would just fly apart. So again, to say that the science can explain everything, it can't explain that. It is out by a phenomenal amount. So they hypothesize, they try to call it a theory, but it's really a hypothesis, that space is not empty. It's full of virtual particles and antiparticles. And when they come together, they form energy, and they call it dark energy, because they don't know what it is. And it comprises 70% of what's going on in the universe. It provides 70% of what's going on. And they're in the dark about it. Now, as the universe gets bigger, there's more space, therefore there's more particles and antiparticles, virtual particles and antiparticles, and more energy. So it's winning over gravity, because the mass of the gravity, which is responsible for the mass is responsible for gravity, and that's remaining both the same. So that's why the universe is expanding. But they also realize that they need more matter, 3 or 4 times as much matter as they can, ordinary matter. So they call it dark matter. Why do they think that? Well, because again, when a skater spins, right, he puts it out his arms, he goes slower, brings them in, he goes faster. Pluto goes slower around the Earth than Mercury. But what happens when the stars go around the center of the universe, the center of the galaxy, sorry, which is a black hole, big black hole? It doesn't comply. It doesn't work right unless you have 4 or 5 times as much mass. They don't know what it is, and they can't see it. It doesn't compose of quarks, atoms, or molecules. So they call it dark matter. And they need 3 or 4 or 5 times as much as regular matter. So you have 95% of the universe that science is in the dark about. And so again, to say that science has the answer for the fundamental questions is really stretching it. They're trying to find the dark matter. I think it may be either machos, massive something, or wimps, weakly interactive massive particles. I think that you're trying it out at CERN and the Large Hadron Collider, and also on the International Space Station. Yet to find. So is it just a theoretical concept, or is it real? Other thing that really can't understand: how do you get all these equations, eke them out from reality or from the universe? You have all these different laws or theories before 1905, conservation of energy, conservation of matter, Newton's law of gravity, force of gravity. And by the way, I didn't mention that he also had the law of momentum. And that, with the law of gravity, explains why things go around. The moon goes around the Earth. He said that things will keep going unless there's something there to stop it. Aristotle said, no, everything stops, comes to rest. You need the hand of God to get it going and to keep it going. And Newton says, no, you only need my 2 laws here to explain how the moon goes around the Earth. Take a cannon and a cannonball up on a mountain, and drop the cannonball down. It falls to the center falls down just like the apple does in the orchard. Shoot it out of the cannon and go a mile, kilometer, or kilometer before it falls down. Shoot it farther and go halfway around the Earth. Shoot harder again, it may go all the way around the Earth before it falls. shoot it harder again and go all the way around Earth. Keep going. And law of momentum would say it's keep going until something that's there to stop it. So it's not, as Aristotle thought. It's the law of gravity and the law of momentum. Besides that, then you have Boyle's law, Jarrett's law, and all the other laws. And after, of course, 1905, you have Einstein's special theory of relativity, E equal mc squared. And you have his special, that's a special, and you have a general theory of relativity. Forces warp in space-time. Explains everything on the massive level. But what if it's the other way around? We don't eke out all those thoughts and equations and reality from the universe. It's the other way around. The universe is derived from them. We create reality now. We create virtual reality. There are concerts with people who are performing, doing a performance after they've died. They use holograms, virtual reality. You don't know whether they clap for them or not because they're already dead, but other than that. We probably need something a little more powerful, a little smarter. Something like omnipotent and something omniscient. Something occurring everywhere, looking, changing all these waves into particles. Something omnipresent, something looking down to keep you from being just purely waves. Before you could have enough actual reality, not just virtual reality, to explain all of the universe. Now, so far, I've just been concentrating on your physical makeup. But of course, you are more than your physical makeup. Lots more. You have your mind, you have your thoughts, I say, you have your interpersonal skills, you have your dreams, and so on. So is there something that, there must be something beyond just the physical makeup? Something maybe the science doesn't really have a grip on. There was an experiment done in Laurentian University. Persinger. He took, at Sunbury, Ontario, he took students, and unbeknownst to what the experiment was going to be about, he put helmets on them. Started off with hockey helmets. And they had magnets on them to measure the brain waves. And then he put them in a isolation booth devoid of any ambient electromagnetic radiation, and deprived them of the sense of sound, hearing, sight, smell, touch, and observed the brain waves. He found that the brain waves on the left side of the brain closed down, and the ones on the right became active. He took them out and asked them what they had experienced, and 4 out of 5 said they had out-of-body experiences. They felt that they were looking down on their body, it had come out of the body and looking down on it. They saw that they had saw tunnels of white light. They felt someone was behind them or beside them. Some said they saw demonic creatures. Some even said they saw God. As a result, it's been nicknamed the God Helmet. So is there another realm other than the scientific or the physical? Well, this phenomena is not only happened there, but it happens with a lot of near-death experiences, documented, thousands. But people have the same type of phenomena, experiences, regardless of their religion, regardless of their culture, regardless of their language, regardless of the countries it came from, and historical background, everything, the same sort of phenomenon. And science really cannot explain that. They attempt to. There's a debate between those that do, can and cannot. Say they can, cannot. And mankind itself has always thought there's something beyond the physical, something that transcends. There's something over and above the physical world. If you like, the mind or the spiritual. Even going back in time, before we established the current religions, and often we refer to them, of course, as pagans, but nevertheless, they always had the concept there's something up above, or something beyond them, and something that looking down at you, aware of you. Home sailors moved in 1492, came to the Americas, and the crew was starving. So he told them, with their spirits, because they thought every object, even inanimate objects, had spirits, would be angry at them, and they, to show their anger, they would swallow up the moon in 4 days. And when the lunar eclipse came in 4 days, he got his food. Now, I've heard that, and I haven't really followed up and to see how true it was, but you can do that. Makes a good story, yeah. And religions, they all have this basic fundamental idea. You might think, there's so many different religions, how can they all be true? Well, maybe they're all, at the fundamental, they all are true. That there is something other than the physical, it's something that transcends the physical. There's something up there that is looking after you and watching you. Maybe something that's changing all the waves into particles. Something, they need something observing them, and maybe it's this phenomenon. Now, some of the, in the past at least, some of the fundamental religions that were fundamental and very dogmatic, they would say, no, my religion is the only religion. In other words, there's your way and there's God's way. But nowadays, no, most religions are more tolerant of the other religions, particularly in the Christian religion, this ecumenical movement, saying that yes, there are some different traditions, for sure, because they come from different practices, but we don't necessarily demonize the other religions, say that they're, one religion still that does that is the Islamic State, where it says that theirs is the only religion, and if you don't follow the practice, you'd better watch out. I think it was Sullivan from the CBC, Canadian Broadcasting Company, interviewed a prisoner in Iraq from the Islamic State, and he said that if you believe in Abraham, you may be allowed to leave, but otherwise you have to convert. If you don't, you will be terminated. Or if you're a woman, you'll be sold into slavery if you're under 40 years old. And the religion states that you have to, what you can think, what you can say, even what you can wear. And if you don't comply, you're in big trouble. Some Islamic states, even now, if you say something against their leader, Mohammed, or the head of state, you have a price put on your head, unless you But most modern religions now, they are more tolerant of all the other religions. And you could say they were all right because they all have the same fundamental uh, belief and dictate. And if you get into the Far East religions like Zen, Buddhism, they try to transcend themselves above the physical through transcendental meditation into the mind of the spiritual world. Then, and even if you don't belong to a not recognized, but a traditional religion, most of the people would say they believe in spirituality. There's something over and above the physical. So looking then how you got here and where you got here and when you got here, maybe now you can say why you got here. When there's something that you can't understand, I think you maybe never understand, you usually say, well, only God only knows what that is, or why that happens, or why it doesn't happen. God only knows. Or something happens that's deleterious, you say, thank God that didn't happen. Could be deleterious. Or something happens that's fortuitous, and you say, thank God that happened. So you can say, thank God the force of gravity exists because it means I can stay on the earth and not fall off. The Chinese will fall off too. Thank God the electromagnetic force is greater than the basic force of gravity. Otherwise, I would fall right through the earth down into maybe a black hole or a singularity in the center of the earth. And God only knows what that is. Thank God the strong force is stronger than the electromagnetic force. Otherwise, I'd fall apart. All my atoms and myself would fly apart. I think there's a weak force to allow the atmosphere to exist and protect me from harmful radiation and objects from space. And thank God every single event that ever happened, as I said, the astronomical amount of things that happened before happened. Otherwise I wouldn't. So whether you believe that you're here because of fortuitous random accidents, happened all those events, or whether you think there was some plan or purpose behind it, as most religious people would say, it's nevertheless miraculous that you're here. Who are you? You are a miracle. End of story.